Hello, this is lecture 1.3C, AP Calculus. We're on page 64 and 65 in your book, and we're just going to continue to work example problems on limits and indeterminate forms, okay? So let's work this problem that's the example of a compound fraction. And we also have another trick that we used to use in pre-cal that I'm going to remind you that you can use. So we need to do some algebraic manipulation here. So first of all, if you plug in 2, you're going to get a half minus a half, that's 0, and then 2 minus 2, 0 over 0. So the plugging in part doesn't work. We got to do more work. So we have the limit as x approaches 2. So the trick on getting a common denominator here is multiply the denominator together. So x times 2. And then bring that 2 up here to the top left and the x up here to the top right. That is the fast way to do this. So that's going to be 2x as our denominator. Going to bring that 2 multiplied by 1. We've got 2. X multiplied by 1 minus x over x minus 2. Now remember, this is like multiplying by 1 over x minus 2 now. So I'm just going to bring that x minus 2 up a level. Remember, you have to write the limit every time. Limit as x approaches 2 of 2 minus x over 2x times x minus 2. All right, now we've got it all into kind of a singular fraction here. But we can't quite cross out. But what you can do is, remember, if you factor out a negative 1, you can switch these two, this 2 and this x. Okay, so let's factor out a negative 1. We have the limit as x approaches 2 of, we'll put a negative out front, and then we can make it x minus 2. That's what we need in order to cancel out the x minus 2. That's on bottom. So if we distribute that negative sign, it would be negative x, negative negative plus 2. So negative x plus 2 is the same as 2 minus x, the exact same thing. So we didn't change anything. We just factored out a negative, reversed those two values, and now we can cancel as long as x does not equal 2, because that would, if x was 2, that would make the denominator 0, right? So now we have the limit as x approaches 2, and with that negative sign, the numerator is now a negative 1 over 2x. And now we can plug in. The 0 over 0 is gone. We have the limit as x approaches 2 of negative 1 over 4. All right, excuse me, we can plug in there. It's not the limit anymore. That's the answer. That is the limit. Okay, we can plug that 2 right in there. Okay? Pretty cool. Algebraic manipulation. All right, let's, you did this on the last homework, but let's do an example of, let's go ahead and give this a title. Difference of two perfect squares. And on the last lecture, I gave you the formula, reminded you a squared minus b squared. You can factor that into a plus b times a minus b. Or a minus b times a plus b. Same thing. Okay? All right, let's look at example 42 on page 65. Okay, so we have the limit as x approaches 2 of 2 minus x over x squared minus 4. And hopefully, so if we plug in a 2, we're going to have 0 over 0. But hopefully you can recognize that x squared minus 4 is two perfect squares. X is x squared. So if you take the square root of that, it's x. Square root of 4 is 2. So that's going to be the limit as x approaches 2 of 2 minus x over x plus 2 times x minus 2. So remember, a would be x, b is equal to 2. Did a lot of that in Algebra 2 also. Now I can't cancel out anything, but if I employ the mathematical trickeration that I used on the last example, we can just factor out a negative, and you've got x minus 2. And if you're not sure if you did that right, distribute the negative sign. You'd have negative x plus 2, which is the same as that. Or x plus 2, x minus 2. So factoring out a negative, then you can just switch the numbers. You don't change the sign. Now we can cross out that x minus 2 as long as x does not equal 2. And we have the limit as x approaches 2 of negative 1 over x plus 2. So we actually ended up with the same thing as the last example in our final answer. And plug in a 2 here, you'd get negative 1/4. All right, that's a good example. Employ two tricks: factoring difference of two perfect squares and factoring out a negative. All right, so all of these are good mathematical algebraic techniques to try to get an answer from these limits. Okay, now let's. I'm going to go ahead and put the formulas, and you do need to know these, have these memorized for the test. Factoring cubes. Okay, let's say a plus b, all cubed, can be factored into a plus b times a squared minus ab plus b squared. All right, the way I remember that middle term is a minus if this is a plus. And then you reverse it, a minus b, all cubed, factors into a minus b, so the first term matches the sign there, and then everything is plus in the second term. Okay, so you got to have that memorized. Let's work an example number 40. We have to factor a cube. This is back a page, so on page 64. And we're going to evaluate the limit as x approaches negative 1 of x cubed plus 1 over x plus 1. So plug in a negative 1, we're going to get 0 over 0. So let's factor the top. And I think I want to apologize for, I think a better way to write this would be a cubed plus b cubed and a cubed minus b cubed. Let's go with, it's a better way to write that, a more correct way. Okay, so here a is equal to x and b. 1 is a perfect cube. You take the cube root of 1, it's 1. All right, so we would have x, this would factor in, and we can't forget the limit as x approaches negative 1 of x plus 1 times x squared minus 1 times x, which is just x, plus 1 squared, which is 1. Right, so in terms of x, I'm just writing this part over x plus 1. So that's pretty easy. Now we can cancel out the x plus 1 as long as x does not equal negative 1. we have the limit as x approaches -1 of simply x squared minus x plus 1. Now we can plug that in. It's not a fraction anymore, so we're not going to get 0 over 0. So that's going to be -1 all squared minus -1. So I'm writing it out so I don't make a mistake with these negatives. And then plus 1. That's going to be 1 plus 1 plus 1, which is 3. I find a lot of times on my tests that the students will do all the algebra correct and in the end mess up a negative sign or something, and I have to count off. And of course I give a lot of partial credit for that. All right, so the summary of finding limits with indeterminate forms all right, ran out of room there. Okay, so first if it's indeterminate, plugging in won't work. So first of all, factor and cancel. That was yesterday's examples, or the previous lecture examples. The common denominator, finding a common denominator. All right, that was one example, yes, on the last lecture, and also the first example today. The rationalization technique. And that is where we use a conjugate to get rid of the radical. Did a couple of those yesterday. And then sometimes you have to use more than one. So how about all of the above? So sometimes you have to utilize a common denominator, factor and cancel. We can even factor, add another bullet, factor out a -1 to flip those terms. All right, so hold off just a second. I'll erase this and write the homework assignment that goes with this lecture. So the homework is page 65. It's really 64. The first one is on 64. So 64 and 65. You're going to do 39. And then 46 through 50, all of those. Okay, and just glancing at those real quick, 39. And I will tell you, let's take a look at 49 and 50 real quick. I don't want this to throw you off. So 49 and 50, instead of using x, uses delta x. Okay? Just think of delta x as an x. Okay? As delta x approaches 0. That's what you're going to be plugging in for. So where everything else is x, in the end, you're going to have some delta x's canceling out. On this. So of course I'm going to work those problems for you, but this is 49 and 50 are foreshadowing for the beginning of chapter 2. So just give them a try. Try your best. Go through the algebraic manipulations on these two, and you will be plugging in 0 for delta x and not x in the end. So you'll get a final answer that might have an x in it instead of just a number. Okay, your final answer on 49 and 50 might have, I don't remember exactly, but it might have an X in the answer. All right, that's all I've got for this lecture, and I will talk to you next video.